Let's say you volunteered. You've agreed to be the subject of the most extreme physics experiment ever conducted. You're going to fall into a black hole. Specifically, you're going to fall into a supermassive black hole, one at the center of a galaxy similar to ours, with a mass several billion times that of our Sun. I chose this size deliberately. You'll understand why in a moment. You're in a spacecraft, positioned a safe distance from the event horizon, the point of no return, the boundary beyond which nothing, not even light, can escape. From here, the black hole looks like nothing. It is an absence, a circle of pure darkness against the stars, outlined by a ring of distorted light, the accretion disk that glows from the material that is being gravitationally tortured into luminous plasma before crossing the horizon. You have a stopwatch. You have a radio link to Earth. You begin your descent. T-minus 60 seconds. The last normal moment. Nothing dramatic yet. You're falling towards something you cannot see. Gravity is increasing, but at this distance and with this mass, the tidal forces, the difference in gravitational pull between your head and your feet, are still within human tolerance. You feel a pull, an acceleration. Your spacecraft's instruments show the increasing curvature of space-time around you. You send a signal back to Earth. Beginning approach. T-minus 30 seconds. Time starts to break. Something strange is happening to your radio communications. Earth's transmissions are reaching you, but they are arriving slightly faster than they should. Not just in signal terms. The photons from Earth are actually blue-shifted and carrying more energy than they had when they left. Meanwhile, your transmissions back to Earth are being red-shifted, stretched, losing energy as they climb out of the increasingly deep gravitational well you are descending into. From Earth's perspective, and this is where the true strangeness begins, you are slowing down. Your radio signals are arriving at longer and longer intervals. Your voice, if you were transmitting continuously, is deepening, slowing, becoming stretched. Time itself, according to the mathematics of general relativity, confirmed by every experiment we have ever run, is passing at a different rate for you than for observers at a distance. You are experiencing gravitational time dilation, and it is about to become extreme. T-minus 10 seconds. The event horizon approaches. Here is what most science videos get wrong about the event horizon. You will not feel it. You will not see a wall. You will not experience a dramatic visual transition. The event horizon is not a surface in any physical sense. It is a mathematical boundary, a point in space defined entirely by the relationship between mass, speed, and the curvature of space-time. When you cross it, nothing in your immediate experience will mark the moment. This is the reason I chose a supermassive black hole for your journey. In a stellar mass black hole, the kind produced by a single dying star, typically a few dozen solar masses, the tidal forces at the event horizon are already enormous. The difference in gravitational pull between your head and your feet at the horizon of a stellar black hole would be so extreme that you would be stretched vertically and compressed laterally, a process physicists call spaghettification, before you ever crossed it. You would die outside the event horizon, pulled apart like taffy. But in a supermassive black hole, the event horizon is so vast, potentially hundreds of millions of kilometers wide, that the tidal forces at the boundary are actually mild, survivable. You cross the event horizon of this black hole, with no physical sensation marking the moment. From Earth, however, you have disappeared. The photons from your spacecraft have been pulled into orbits that will never carry them away from the black hole. You are, to any external observer, frozen at the edge of the event horizon, red-shifted into infrared, then radio waves, then silence. You appear to hang there, frozen, forever, as you slowly fade below the threshold of detection. To you, this takes no time at all. Inside, minutes to singularity. You are now beyond the event horizon. Physics is doing something that has no analogy in any human experience. The direction toward the singularity has become a direction in time, not in space. In normal space-time, you can move freely in 3 spatial dimensions. In space, you have choices. Inside the event horizon, the singularity is not a place ahead of you. It is in your future. The mathematical structure of space-time inside a black hole makes approaching the singularity as inevitable as tomorrow. But you cannot steer around it any more than you can choose for tomorrow not to come. What are you experiencing? Tidal forces are increasing. Not yet lethal. The mass of this black hole provides a relatively gradual increase, but increasing. You're beginning to feel a stretching sensation along your spine. Mild, curious. Outside your window, if you look outward, back toward where the event horizon was, the universe is visible in a strange circle above you. The light that enters the event horizon from outside continues to fall inward, which means you can still see the rest of the universe, but its appearance is bizarre. The entire sky is compressed into a smaller and smaller circle above you. Stars that should be in all directions are clustered into a shrinking bright spot. You are watching the entire history of the universe's light, all future photons that will ever enter this black hole, arriving in a compressed stream from that circle. Time outside is moving infinitely fast relative to you. You are watching the universe age. The question physics cannot answer you are approaching the singularity. The singularity is where general relativity, Einstein's theory of gravity, breaks down. At the singularity, density becomes infinite. Space-time curvature becomes infinite. All the equations we use to describe reality produce the number that mathematicians use to politely say, "Our model has failed." Infinity. This is the honest answer about what happens to you at the singularity. We don't know. General relativity predicts a point of infinite density at the center of a black hole. But infinite density is a symptom of a model reaching its own limits, not a description of physical reality. The theory tells us it doesn't know what happens there. Quantum mechanics, which governs the behavior of matter at the smallest scales, should also apply in this extreme environment. But quantum mechanics and general relativity are currently incompatible theories. We have not yet produced a theory of quantum gravity that can describe what actually happens at the center of a black hole. This is one of the most important open questions in all of physics, and we don't have the answer. The observer on Earth. What they see. Let's return to Earth for a moment and consider what's happening from outside. An observer watching you fall toward the black hole sees something that feels like science fiction, but is physics. They watch your spacecraft slow. They watch your transmissions become more and more stretched. The light from your ship is red-shifted, shifting from visible to infrared to radio waves. You appear to freeze at the event horizon, your image dimming, the color draining from the light you're emitting. Eventually, the light from your frozen image falls below the threshold of detection. You blink out. But you never, in any technically physical sense, cross the horizon from their perspective. You are, from the external reference frame, frozen there forever. Who is right, you or the outside observer? This is not a contradiction. Both observations are correct within their own reference frames. General relativity doesn't privilege one observer's experience over another's. In your frame, you crossed the horizon and fell toward the singularity. In their frame, you never crossed at all. Both are equally valid physical descriptions of what happened. Reality, inside a black hole, is literally different depending on where you're standing. The Hawking problem. There's one more thing to address, and it is currently one of the most debated problems in theoretical physics. Stephen Hawking proved in 1974 that black holes are not perfectly black. They radiate. Quantum mechanical effects at the event horizon cause pairs of particles to form spontaneously. One falls inward, one escapes. Over an extraordinary length of time, for a supermassive black hole, longer than the current age of the universe many times over. This Hawking radiation causes the black hole to lose mass and eventually evaporate. When it does, what happens to the information about everything that fell in? According to quantum mechanics, information cannot be destroyed. The information about the state of every particle that ever fell into a black hole must exist somewhere in the universe. But if the black hole evaporates and the Hawking radiation it emits is random, as Hawking originally calculated, then the information is gone. Permanently, forever. This is called the black hole information paradox, and it has occupied the best minds in physics for 50 years. Hawking himself reversed his position before his death, arguing that information was preserved, though the mechanism remains disputed. Juan Maldacena's ADS/CFT correspondence offers a possible mathematical framework for how information could survive. The debate continues. What the black hole actually tells us. You agreed at the start of this video to fall into a black hole. What you found there, besides an extraordinary end, was a series of places where our best physics runs out, where our models produce infinities and contradictions, where the two great theories that describe reality at its largest and smallest scales collide and neither wins. Black holes are not just extreme physical objects. They are the universe's way of showing us where our understanding ends. They are the signposts pointing to the physics we haven't built yet. And that, more than the darkness and the singularity and the spaghettification, is the most terrifying and the most exciting thing about them.